Okay, so in this here, we're going to talk about some of the geometric applications of the first and the second derivative of a function of x. And we have seen in previous videos that we can derive a function twice to get the second derivative, but we haven't really discussed what the geometrical meaning of that second derivative really is. And that's what we're going to be doing in this video. But before I explain what the second derivative is, I want to talk about something that is related to the first derivative. So let's suppose that we have some function that goes like this. So let's call this f of x. Now we know that the first derivative represents the gradient at any specific point that we choose, and the gradient is simply a tangent line to that curve at that particular point. So we can see that the gradient is going to be continuously changing with the function, and the value of that gradient is actually going to tell us whether the function is increasing or decreasing at each point. So to show you how that works, we can define this as when the first derivative is greater than 0, then what is happening to the function? Well, if you have a positive gradient, then that means that you're actually going in this direction, you're increasing. So this is increasing. Increasing. And what does that suggest about the function? Well, it's just increasing, right? So what happens if you have the case the derivative is less than 0? Well, that should tell you that it is actually decreasing, because if you have a negative gradient, then that means that the gradient is actually going down like this, and that means that the function, the values of the function are moving down. So that's going to be decreasing. And finally, what happens in the case where you have the derivative equals to 0? Well, that's an interesting one, because if the gradient is equal to 0, then that means that your gradient should be horizontal. And if you have a horizontal gradient, what's happening to the function? Well, there are two main things that could be happening. One of them could be that the function is changing direction like this. So it is coming from the bottom, it is increasing, and then the gradient starts to decrease until it comes to 0, and then the function continues to decrease. That's the only case in which you can have a horizontal gradient like that. Or you may have something that is the opposite of that. You may have a function that is coming down from the top and then goes up again. So you could also have that. So in general, we call this a stationary point, because it is a point in which the gradient is 0, so the function is neither increasing nor decreasing. It is simply stationary at that point. And then what is going to determine in which direction it's going to go is the gradient at the points around that central point that we call the stationary point. So these are the main three definitions that we need to take into account, because this is going to be important for defining the second derivative. Stationary point. Alright, so having defined this, what can we say about the second derivative? Well, obviously this would be quite useful, because if you have a function like this, you know that when the gradient is horizontal, you actually are at a point where the function is changing direction. And this here, if you look at it from a very limited domain, you see that this is a maximum point, because it is the highest value of the function f of x that you can obtain within this local domain that we choose here. Obviously, after it past this point in x, obviously the values of the function are going to keep increasing and are going to be higher than this maximum. But if we constrain our function to something like this, to this domain, we can see that this is the local maximum within this vicinity. And likewise, this would be the minimum in this local vicinity. So we would call this a local maximum and a local minimum. But this particular definition doesn't tell us which one is the maximum and which one is the minimum, because it doesn't really distinguish between the two. So there's another thing that we can do, and the second derivative is actually going to tell us whether those points are a maximum or a minimum. So second derivative is defined as follows. If the second derivative is greater than 0 at that point x, then we have a function that is concave up, concave up, and that essentially means we have a minimum, because concave up means this, so that has to be a minimum. and we usually refer to it as a local minimum. If we talk about a maximum or a minimum that spans the whole function for all values of x, we'll call that a global maximum or minimum. Now, if the second derivative is less than 0, we have a function that is concave down at that point, and thus we say that this is a maximum. And there's one more case. What happens when the second, when this is equal to 0? Well, we call this an inflection point. And there are two ways to spell it. It's either like this, or in some countries it is actually spelled with an X. So it's either an inflection point in general. So what is an inflection point? Well, imagine you have a function that is changing direction, but it doesn't actually change direction at all. So this function, for example, is coming like this. It has a gradient that is very steep, very high. Then the gradient changes and it starts to decrease. Then it decreases until it reaches a point in which it is almost horizontal. But then instead of going down, it continues to increase again. So this would be a function like x cubed by itself, because it goes through the origin and it doesn't actually go back down. It just keeps going up like that. So what would be the inflection point? Well, inflection point is a point in which there is no maximum or minimum, but rather the function is changing direction from decreasing in the gradient to increasing in the gradient again without making this kind of turn. So this would be an inflection point. And we can have vertical inflection as well. So if you had a function that went like this and you had a line that was going straight down, that would be an inflection point as well. And it doesn't need to be perfectly horizontal or vertical. It could be anything. It could be something like this. So just to give you an example, let's have a function x, y. Let's have a function that goes like this. At some point here, we would have an inflection point, because this is where the gradient would go from decreasing to increasing again. So what determines this is the points in that proximity, so the points to either side of that point of inflection, are the gradient at those points are going to tell us whether this is a point of inflection. And there's usually a little table that you can draw to test that. You can have your values of x, your values of y, and then you can also have, say, your values of f of x, so f prime, and then you can tabulate them. So let's say your point of inflection is here somewhere. Then you would choose values around that point. So let's say this is 0, then you would choose point -1, 1, 2. And then you would do the same. You calculate the gradient for each of those points, and you would see if the gradient seems to follow that pattern where it decreases and then it continues to increase after the stationary point or the inflection point. Then you would know, okay, this is an inflection point. And that's one of the ways you could check that, by drawing that little table of values. But in general, this tells you enough information you need to know about the nature of that function. So let's apply this to an actual example now, just to see how all this comes into play. So I'm just going to move up a little bit. I'm just going to erase this. So these definitions are very important, because these are the geometric applications of calculus. And in the following videos, we'll see how this can be applied to other cases as well. So let's say you have a function f of x equals to x cubed plus 2x squared minus x plus 5. So let's find the derivatives first. F prime would be x squared, 3x squared plus 4x minus 1. Second derivative will be 6x plus 4. Alright, that's all good. Now we want to find the stationary points first, so that means we need to set this function equal to 0. So we're going to have 3x squared plus 4x minus 1. Now we got to find the roots, the points x that will give us that stationary point. So we're going to use the quadratic formula. We're going to have minus b, which is in this case minus 4, plus or minus square root of b squared, which is 16, minus 4 times ac. C is minus 1, a is 3. So we have that there, and this is divided by 2a, so that's 2 times 3. So this is going to be minus 4 plus or minus square root of 28 over 6, which simplifies to minus 2 over 3 plus or minus square root of 7 over 3. So these are our two stationary points. That's the coordinates of x that will give us a stationary point for this function. So what we do now is we're going to plug these values into the second derivative equation, and that's going to tell us which one of them is a maximum and which one is a minimum. So let's start with minus 2 over 3 plus square root of 7 over 3 equals 6 times minus 2 over 3 plus root 7 over 3 plus 4, and that's approximately equal to 5.2915. And you notice that this value is actually greater than 0, so this implies this point is a minimum. Now we're going to plug the other value into the same equation, so it's going to be minus 2 over 3 minus root 7 on 3, and this is going to be approximately equal to minus 5.2915, which is less than 0, and this implies this would be a maximum. So if the maximum occurs at a point that is to the left hand side of the xy plane, then we could sketch this curve just from this information without having to calculate the other values. If we wanted to find the actual maximum and minimum values, what we would do is we would take this, so the maximum value is this one, we would plug it back into f of x, and then that would give us the maximum value at that point, or the local maximum, I should say. And if we wanted to get the minimum, we would plug this value into f of x to get that local minimum value. So if we wanted to sketch this curve, it would end up looking something like this. So we would have our xy plane. So to the left hand side we would have the local maximum, and to the right hand side we would have the local minimum. The interesting thing though is that they're equally spaced from the origin, so we can assume that somehow this should go through the origin, but we can also check that by making the necessary calculations there. So the function would look like this, and it would have some symmetry of some sort. It doesn't need to go through the origin, but this is just to sketch the function of what it would look like. So in the next video we're going to talk more about what these concepts are, and we're going to talk about other geometric applications of the derivative and the second derivative.